Okay, you can go.
Okay. Ciao a tutti. Welcome to the first meeting of the 2026 Ithaca Fest. It is my pleasure to introduce our first speaker, Cipriano Cioffo from University of Pisa. And Cipriano, the title of your talk is The Exact Completion of Fibration. Please, Cipriano.
So, thank you. Hello, everybody. So, it's a pleasure for me to talk for the Ithaca Fest 2026 and to present this joint work in progress with Mili Maietti, Samuele Maschio, and Pietro Sabelli. So, you already know the title, you can read the title. It's about exact completion and fibrations. And I would like to start with the following question. So, do we need a theory of exact completion of fibrations? So this is there is a very simple example that we can consider for, as the simplest one, which is the codomain fibration of a category with finite limits. I will denote Lex category with finite limits during this talk. So what we can do with category with finite limits is to consider the codomain fibration. Then what we can do is to apply the exact completion of the category B, and then in turn consider the codomain fibration of the exact completion. So what we can observe about the codomain fibration of the exact completion are some interesting properties. For instance, the fibers of these fibrations are exact, the reindexing functors are exact functors, of course the base category is exact, and there are also many other interesting properties that we will see throughout the paper, the talk. So what I want to argue is that the codomain fibration of the exact completion of the category B should be considered as the best candidate for the exact completion, whatever it means, of the codomain fibration of the category B. So if we look at this example, it seems that we don't have really a problem since we can consider we can rely on the exact completion for one categories. But this is not the end of the story because things change when we consider sub-fibrations of the codomain fibration of our category B. Indeed, if we play again the game of the exact completion and its codomain fibration, what we expect is to lift the fibration P that you see on the left to the right triangle. So what we want to do is to fill the right triangle in a suitable way. So to correspond to the fibration P, another fibration which in a suitable way. So this is not a random question that we asked ourselves. Indeed, it is a question that we asked in order to generalize our key example of this situation, which was the case of the predicative effective topos introduced by Emilio Maietti and Samuele Maschio in the 2021. So the predicative effective topos is a constructive predicative variant of Ireland effective topos, which is built in a constructive and predicative meta theory such as ID1-et. So what Millie and Samuele did was to define the predicative effective topos as an elementary quotient completion, in this case an exact completion of a suitable category, here denoted with C. So what happened in this second work, which I collaborated with them during my postdoc in Padua, was to describe the fibration of sets for the predicative effective topos. Indeed, on the left, they identified two structures, one for dependent sets of the category C and one for dependent collection. And what we did was to lift the fibrations of sets from the left triangle to the right one. And what I think is that at the end of that work, since we were providing it explicitly, it was a common feeling that what we did for the predicative effective topos could be generalized. And so the question that I asked in the second slide, and was part of a more general picture. That is the one that I would like to give you during this talk. So In order to do that, I will exploit the syntax semantics correspondence between categorical structures and type theory. I will use sometimes the language of type theory and sometimes the language of category theory, and I will try to give some correspondence between these two formalism. So I'm referring to the correspondence that you can find in the paper by Emilio Maietti, which is called modular correspondence between the internal language of some categories and some categories given in terms of type theory indeed. So if you are not familiar with type theory, consider that you have types, dependent types, terms, and these are usually understood in the categorical language as object, arrows, section of arrows. And what Millie proved was to show that the internal language, the internal type theory of suitable categorical structure, for instance, for category with finite limits, which correspond to extensional Martin-Löf type theory with sigma types and one type. That what I will do is to recall the notion of setoids and its categorical counterpart of pseudo-equivalence relations, and then I will recall the notion of families of setoids before looking for a categorical descriptions of them. Because what we want to do, is to fill the triangle that we saw at the beginning of the talk using a categorification of the notion of families of setoids. So let's start to go into the details. Setoids were introduced by Bishops in his work Foundations for Constructive Analysis, and they are given by a type, closed type X, and a relation R, which depends on the type X twice. So if you are not familiar with the type theoretic language, the column symbol should be interpreted just as an apartness relation. So x1 and x2 are two terms of the type X. So the relation of the setoids is an equivalence relation, which means that we require a proof term called ref, which witness the reflexivity of the relation, a proof term sim, which witness the symmetry of the relation, which means that if you have a proof term of the fact that x1 is a relation with x2, then the symmetry is a proof term of the fact that x2 is in relation with x1. And then we also require the transitivity proof term, which, as you expect, turns two proof term of the fact that x1 is a relation with x2 and x2 is a relation with x3 into a proof term of the fact that x1 is a relation with x3. So then when you consider setoid arrows are just terms in the proper context of the type of the second setoid, of the codomain setoids, such that they respect the relations and moreover they are considered up to functional extensionality, which means that you can prove that there is a proof term of the fact that the image of two arrows are in relation. So if you go through syntax and categorical language for category finite limits, you obtain that the corresponding concept for setoids is given by pseudo-equivalence relations. And the pseudo-equivalence relations were used by Carboni and Celamagno to provide an explicit description of the exact completion of a category with finite limits. So very quickly, pseudo-equivalence relations are given by a pair of arrows, R0 and R1, three witness of the fact that this relation is reflexive, symmetry, and transitive, and arrows are given by arrows between the base object of the relation, such that there exists another arrow G closing these two squares and making them commute. Again, for the case of the exact completion, we have that the morphism between pseudo-equivalence relations are considered to the following relation, which is called the alpha-modo-p relation. So, as I told you, there is this correspondence between the syntax and the categorical structures. Setoids correspond to pseudo-equivalence relations. We can use setoids to work to exploit the exact completion of a category. And what we want to do is to extend such correspondence to families of setoids, which are a more involved structure. Indeed, families of setoids constitute of the following data. We have a base setoids x and r, and then for every element of x, we have a setoids which depends on it. So we have a of x and s, which is a relation on a of x. But the most important point of families of setoids are the transport map. So the transport map are functions which takes into account a proof term of the fact that x1 and x2 are in relation and provides you a function between the corresponding dependent setoids, so ax1 and ax2. These transport maps need to satisfy some properties. The first one is the proof irrelevance, which states in very simple terms, states that the action of the transport map does not depend on the proof term that you consider. The second one is the fact that transport map preserves the relations of the setoids, and the third one is the unitality condition, which says that which states that the transport map on the reflexivity term acts as the identity arrow. So what we want to do for the rest of the talk is to give a suitable categorical description of families of setoids in order to build the fibration that we are looking for at the beginning of the talk. So probably is a good moment if you want to ask some question before I go on.
Cipriano,
Yes.
I think that in the definition of a pseudo-equivalence relation, the direction of W is wrong.
The direction of?
W.
Yeah. Yeah. Thank you.
Okay.
Thank you. Okay, so let's try to give a suitable categorical description of families of setoids. So in order to do that, what we did was to start from some intuition slash folklore statement about families of setoids, which are which are usually considered groupoid actions. So the point is that before going into the details, recalling the notions of groupoid action, is that our wish, remember that our wish is to give a description of families of setoids from below. What does it mean? We are still starting from a fibration, the fibration P at the beginning of the talk. We won't use that data to provide a new fibration on the exact completion of B. But there are some problems if you try to use directly groupoid actions. The first one is that setoids and pseudo-equivalence relations do not provide groupoids. And the second one is the proof irrelevance of transport maps, which is a condition which does not follow from the usual conditions of groupoid actions. But in order to understand what I'm saying, let's recall very quickly what is an internal groupoid and an action of an internal groupoid with respect to a fibration. So an internal groupoid is a diagram into a category B with finite limits, is a diagram such as the one that you see on the screen. So we have an element D0, which plays the role of your objects of your internal category, internal groupoid. We have an element D1, which plays the role of your arrows of your internal category. And then we have this pullback, which just give you the composable arrows. And then you have many structural arrows that you can figure out what do they mean. So the D and C are respectively the domain and codomain. M is the composition. And of course, they have to satisfy some equality conditions. Okay? So what happens? If you try to fit a setoid or pseudo-equivalence relation in such a diagram, you see that those equalities that the quality that satisfy internal groupoids are not satisfied in this case. And this is why, because the composition for setoids are given by the transitivity proof term. And the transitivity proof term does not respect, you have no conditions that allow you to say that the composition is associative or that the composition with identity, which is given by the reflexivity term, is the identity action. So this is very a pity because the notion of groupoid actions, there is a huge literature about groupoid actions, like internal category actions. For instance, you can see the works by Janeliz and Tolen, but there are many, many references. And they is a beautiful concept which almost capture families of setoids. So if you have a fibration which is cloven, and for readability I will assume that is split, so an action is given by an element in the fibers over D0, an arrow which plays the role of the transport map, D1 over D1, and two coherence conditions. The one for the composition, for the composition, and the other one for the identity. So the point is that this notion does not capture families of setoids, even if you drop the requirements of the qualities between the structural arrows of your internal diagram. And this because you can also try to avoid them, but then what happens is that the conditions that you have on the action are not enough to capture the proof irrelevance of families of setoids. So it becomes an additional condition that you have to add, and things are a little bit cumbersome in this way. So what we did was to change perspective and to adopt a geometrical slash combinatorial view of setoids, exploiting two truncated semi-simplicial objects. So a two truncated semi-simplicial object is just a controvariant factor from the category delta plus 2 into your category, your target category B. So delta plus 2 is the category arising from this diagram. So 0 is just the list with 0 inside, 1 is the list with 0, 1 inside, and 2 is the list with 0, 1, 2 inside. And these that you see are non-decreasing arrows. So what happens? When you apply when you consider a two truncated semi-simplicial objects, so when you have a functor such as x, the arrows that you have are reversed in the direction. And you still have an element here, x con 0, which plays the role of your object. You have an element x1 which still plays the role of your arrows, but this time x2 does not play the role of composable arrows, but x2 should be thought as two cells, two solid diagrams, two solid triangles like this one. So the arrows that you see here, for instance, x1, 2, is just the arrow which takes a 2 cell and gives you the 1, 2 edge. So 0, 2 is the 0, 2 edge, and 0, 1 is the 0, 1 edge. And similarly with these two arrows. And what happens is that two truncated semi-simplicial objects are a very handleable concept, because we can require some additional condition on them. The first one is the can condition. So we require that these objects are can objects, which means that some canonical arrows are split epimorphism. And what does it mean? To give you an intuition, what is required is the following fact. We require that every time we have a horn, like the one that you see on the right, we can fill it in a two complex. Okay? This is, for instance, the condition for the case n equals to 2, but then you require also equal for the n equal to 1. And this is the condition that gives you the reflexivity, the symmetry, and the transitivity term of the setoid. Moreover, we also require a codiscreteness condition, which in this simple case corresponds to the fact that the element x2 is given by the limit of the solid diagram that you see on the screen. So x2, which are our two cells, correspond to triples of proof terms that are compatible with domain and codomain. Okay, so we call such two truncated simplicial objects setoid objects. So two truncated simplicial objects that are can objects and codiscrete. And then what we do, we consider category of setoid objects where arrows are just natural transformation up to the following equivalence relation. And what we obtain is a category, setoid B, which turns out to be equivalent to the exact completion of the category B. And this was very exciting for my point of view, because now we have the right object that we can use to express families of setoids. Indeed, what we can do is to exploit a different notion of action, can be found in this article by Daskin. And at this point, I have to thank Enrico because more than 1 year ago, I was looking for this reference, but was actually impossible to find. And it turned out to be that Daskin was visiting Louvain-la-Neuve probably in that period, and Enrico was able to find a copy of this reference. And in this reference, you see a notion of action on three truncated, whatever is not important at this point, simplicial object. We will focus just on setoid objects, and is given by an element again a transport map sigma, and two coherence conditions. And this time they are enough to capture all the conditions of families of setoids. Then what you can do is to bundle all these actions together and to obtain a new fibrations whose base category is the category of setoids objects. So this is not yet the setoid fibration, because the setoid fibration is a two-step construction. So the first one, we start from our fibration P, then we consider the contravariant functor, which is equivalent by the corresponding contravariant functor given by the Grothendieck construction, and we post-compose it with the setoid construction, which means that we are adding quotients to the fibers. Okay, so this is a sort of fibered exact completion. Then we consider actions over this composition, and what we obtain is a fibration that we refer to as a setoid fibration. Okay, so this is now our tool, and we want to prove that this is a universal construction. In order to do that, we have to find the suitable categorical, the two categories involved. And in particular, we have to define what we mean by lex fibration with comprehensions, and what we mean by exact fibration with comprehension. So lex fibration with comprehension is just a fibration with full comprehension, such that the category B has finite limits, the functor is fibered lex, which means that the fibers have finite limits and the reindexings preserve them. And then we also require that the comprehension functor preserve the structures of the fibers. Then we define the exact fibrations with comprehensions. So, as you may expect, we still require full comprehension, the base categories to be exact, the fibration to be fibered exact, the comprehension to be to preserve the structure, but in addition, we have to require the following descent condition, which is also referred to as modified transferability condition in the works of Janelitz and Toller. So what we require is that for every regular epimorphism Q, if we have an arrow F such that the pullback is in the replete image of the comprehension functor, then F was already in the replete image of the comprehension functor. And with these two categories, what we are able to prove is that the setoid construction provides a left-B adjoint to the forgetful functor U. And this is the main result of this work. So let's see some examples that we have already seen during the talk. The first one is a sanity check that we did, which is the following. If we consider the setoid fibration of the codomain fibration of a category B with finite limits, then what we obtain is something equivalent to the codomain fibration of the exact completion of the category B. This is a sanity check. That's something that we expected. So we are happy with this. Then we have some syntactical examples. For instance, you can consider an intensional Martin-Löf type theory with sigma type, unit type, and identity type, and consider the fibrations of closed types and dependent types. So if you apply the setoid fibration construction, what you obtain is something equivalent to the fibrations of dependent setoids. And it is particularly important because when you have a distinction between small and large types, for instance, when you are assuming a universe, what you obtain is that the fibration of small dependent types, which means that you are assuming dependent types which are small over types which are large, also large, and you apply the setoid construction fibration, what you obtain is the fibrations of small families of setoids, which means that the base type of dependent setoids and the relations are small. And the third one, the most important one, it was to prove that the fibration of sets for the predicate effective topos is an instance of the setoid construction for the fibration arising from the fibrations of dependent sets on the category of realized collections. So let me conclude with some future works. This work has opened a lot of possible different direction of research. The first one is that it seems that the assumptions of full comprehensions seems possible to be avoided. So I have to say that at this point, the assumption of full comprehension really helps a lot in the proof of the main results. But the idea is that relying on some descent calculus, we can drop that condition and prove the same statement just for fibrations, which are lex fibrations and exact fibration. The second future work that I want to tell you about is about a conjecture that I have, which is the following one. So we have seen that setoid objects correspond to the exact completion of one category. So setoid objects are two truncated simplicial objects satisfying the codiscrete and can condition. So my question is, what happens if we consider three truncated simplicial objects? Do they provide a to-one exact completion of a one category which has finite limits? So it should be nice to see if it works, and if someone is interested or knows already the answer, please contact me, because it does not seem easy for me to answer to this question. And then we have the last future work, which is the most important one in the sense that it closes the circle of the motivations that I gave you at the beginning. So what I want to say here is that when we were working with the fibrations of sets for the predicate effective topos, what we wanted to obtain were models of the minimalist foundation, was a model for the minimalist foundation, which is this constructive and predicative foundation introduced by Mili Maietti and Giovanni Sambini in 2005, and then fully developed by Mili Maietti in 2009. So what I have to say is that at this point, our construction is a machinery which helps, let's say, to find models of the minimalist foundation, but not in its full strength, in the sense that what we are assuming implicitly is a sort of proposition as type paradigm. Okay, so instead to look for models of the minimalist foundation in its full fragment, we should be able to obtain a logic which is primitive in some sense. And what we should be provide is a generalization, a fiber version of the elementary quotient completion, which was introduced by Milli, Maietti, and Pino Rosolini in 2013. So what we expect is to consider another subfibrations of our subfibration P, which plays the role of the logic, and then consider families of setoids in which you can ask for the relations to be small or not. And that is all I wanted to say, and I thank you for the attention.
Thank you very much, Cipriano, for your talk. Any comments or questions from the audience? If not, I can ask a question. Maybe related to the third point for future works. In any case, in general, so you use the exact completion of a left exact category, but having in mind your thesis, my question is, there is any reason, interest, or reasons to use or not to use the exact completion of a weekly lex category?
Okay. Well, I have thought about that very quickly once, but the problem is that let's say very simple case. If we have a category which is weakly lex, do we still have that the codomain functor from the arrow categories of fibration? It's a sort of weaker version, no, of fibration because you don't have the uniqueness properties of Cartesian mediating arrow with Cartesian lift, no? So it would be interesting, but for me at least, just to know if it's possible to generalize to the case of the weakly lex case of the exact completion, but I don't know if it is of interest and in the sense that there are examples in which you can see such such construction to be worth, eh, let's say in this way.
Okay.
Can I say something? Can I say something? Maybe. I don't know.
Yes, but maybe there is a question before Millie. There is a coming.
Sorry.
So please.
Hi, Cipriano. Great talk. I really enjoyed it.
I can.
This is referring to your second point. John Burke and Richard Garner have a paper on two-dimensional exact completions.
Mm-hmm.
And in that paper, they show that if you have a one category E with pullbacks, then taking internal categories to that is a kind of two exact completion.
Mm-hmm. Yes, I knew something about that, but they are not exploiting this kind of setoid stuff, right?
No, they're not. No. But if you like consider like a 2-1 category instead of a 2 category, then you get groupoids internal to E instead of categories internal to E, and that's kind of 3 truncated simplicial objects,
nice.
I guess. So I guess that's related to your second question, definitely.
Yes.
Yeah.
Thank you. I have to understand properly that paper. It's not easy.
Okay, thank you, Millie.
I was just to say.
I cannot hear you, Millie.
To say that the weekly legs are important because when we, I don't know, I don't know what happens. Also. I don't.
Millie, try again.
Hello? Do you hear me?
Yes.
No?
Yes.
Okay. Yeah. It's very important to pursue this work also in the case with the weekly lex category because when we go to slice of the quotient completion, let's say we go into in our examples we start from weekly lex category which do not have products when we go in the slice of the base categories, and then to get a full picture we will have to use also to consider completion on weekly legs. And this is also important to close the picture if we want to generalize the proof of the closure of the quotient completion, the exact or elementary quotient completion, under I would say, function space. So Rosolini and Fabio Pasquali, we saw that the real notion of weakly lex locally Cartesian closed category for the case of for our case, which has to be generalized to the elementary quotient completion, really the nice elegant picture requires to work with categories with weak products. So this is also in the list of future work.
Thank you.
Okay, other questions or comments? If not, we can conclude that Cipriano, you have still some work to do with good, I think, good suggestions.
Can we ask one more question from here? Sorry.
Oh, sorry, please.
Yes, I was wondering if there are algebraic examples. For instance, the codomain fibration, in the case of groups, you can make of it the category of black modules, or still a fibration. And I was wondering if there is any application in some similar algebraic static.
So Beppe, thank you a lot because I'm actually looking for algebraic examples. So it's something that I can ask you probably in an email if you can give me some suggestion. But yes, we were looking for something like that. Thank you.
Maybe a variation of what I've said can be of interest. So taking the back modules and the construction on the codomain fibration. So this a Billiard group on the slice, and they stick together with the routine deconstruction. And this is quite common in cohomology of groups, for instance. And variation of this can be of interest. I don't know.
Very good to know. Thank you. I will check it.
Other questions?
Yeah, maybe on what Beppe mentioned, because I had a similar question, but I didn't know how much Cipriano and the others are interested in additive examples. Because there, especially in the direction of your conjecture number 2, there might be something done very recently in the last 5 years in the higher category literature that tries to study exact completions of an infinity category. And there are a couple of references that I can give you if you want.
Yes,
but I don't know how much you're interested in that.
Yes, actually, you're probably referring to a paper by Nicola Gambino, Zumilo, and many other collaborators in which they have a conjecture for the infinite exact completion, right?
No, not exactly. I was thinking about, but maybe exactly. There is a problem of terminology because there is a thing in that people that do stable homotopy call exact completion or exact category, but it's a different notion of exactness. It's a quality exactness. So those are natively additive examples that probably you might not be entirely interested in. At the same time, I think that some techniques might look alike because in the end, you are looking at a finite limit category with bells and whistles attached. And they prove, for example, that the analog of derived categories or something akin to derived categories behave. They have the universal property of exact completions. It might probably be mildly related with what Beppe was saying in a higher homotopy coherent setting, but I don't know. I don't know much more than what I just said. I can just drop you a couple of papers if you think it might be interesting.
Thank you a lot. Thank you.
Good.
Okay, thank you. I think that it is time to pass to the second talk. So thank again.